Okay, so the very last thing I want to go over for this unit is nuclear fission and nuclear fusion. So I want to go over what the difference is between these two and what happens in each process. So when we think about nuclear fission, remember the I. The I is also in splitting. So here we actually have a nucleus that's splitting apart. So the nucleus that we start out with is typically very heavy, a mass number greater than 200, and it divides into smaller nuclei of intermediate mass. And we also typically see one or more neutrons. So a lot of energy is released. And the first element that we knew of that underwent nuclear fission was uranium-235. There are other elements that will fission, but this was the first one we discovered. So to induce fission, we have to have a free neutron absorbed, and it's very easy, relatively easy in heavy elements. So if we have elements heavier than iron, we have a lot of energy that's out as a product. If we have elements that are lighter than iron, we actually have to add energy for it to occur. So those are not as efficient. The common fuel sources that we see in nuclear reactors are uranium, and plutonium also will undergo spontaneous fission. So when we have fission, we do get two new radioactive nuclei. We also typically have 2 or 3 free neutrons. We also produce a lot of heat and some gamma radiation and a ton of energy. And this is just a typical fission reaction. Here we have uranium-235 splitting up into barium and krypton, but there are other pathways for fission for uranium. So what we also see is the sum of the mass of the products is less than the original mass that we started with. This missing mass is a very small amount. It's only 0.1% of the original mass, but it's all converted into energy through Einstein's famous equation, E equals delta mc squared. So we have the mass being multiplied by the speed of light squared. That means a small amount of mass is turned into a huge amount of energy. So when we look at it, if we only need about 1 kilogram of matter converted energy to get the same amount of energy released as 22 megatons of TNT, so huge amounts of energy released. So here we have a neutron hitting uranium-235, causing a fission and producing, in this case, 3 new neutrons. Those neutrons can then hit other uranium-235 nuclei and cause them to fission, and then you start getting the conditions necessary for a chain reaction. So a nuclear chain reaction is self-sustaining. The minimum amount of mass that we need to create these conditions is called the critical mass. So if we don't have a critical mass, the reaction will just kind of fizzle out and it won't be self-sustaining. So here we have a non-critical mass. We have a neutron hitting a nucleus. It's producing more neutrons, but then they run out of nuclei to then hit, so the reaction kind of fizzles out. If we have enough nuclei present, each one of those released neutrons has another nucleus to hit, and you have self-sustaining chain reaction. The other process that we see that is fusion. Fusion will occur on the sun and other stars. We've also produced the conditions necessary for fusion in a hydrogen bomb. We have not been able to control fusion here on Earth. So this when it does occur, it's going to be in the sun or other stars, or like I said, a hydrogen bomb. So here we have 2 nuclei combining. So if we look at the word fusion, it has a U. Uniting has a U. So here we have deuterium and tritium, 2 different isotopes of hydrogen combining to form helium. And we also produce more neutrons, and a ton of energy. So this, unfortunately, we can't do on Earth, but it would solve a lot of our energy problems because you don't get the products of this reaction that are also radioactive. There aren't radioactive materials produced in this reaction. So temperatures necessary for fusion are greater than 10 million degrees Celsius, like we see on the sun. We also have a plasma that we're working with, so this is difficult to work with. So plasma is a state of matter where electrons have been removed from the atomic nuclei. So you have the positive nuclei and you have the electrons. They're all charged. Very, very difficult to contain, very difficult to work with, especially those high temperatures.